Hi, this is Brendan Calloway and Bradley Johnson. We've done a heat transfer project where we analyzed the effectiveness of a subterranean heating system for a greenhouse in Rexburg, Idaho. The greenhouse in question, you can see in the image behind us, is a 6 foot by 6 foot by 8 foot greenhouse on my mother-in-law's property. It's currently out of operation because it's ineffective, especially in the winter when it gets too cold for the plants to survive. We're hoping to determine if we can maintain operating temperature in the greenhouse on the coldest night of the year in Rexburg, Idaho by cycling air through underground pipes. In order to determine the heat transfer that we will obtain with an underground piping system, we had to look at the soil temperature at different depths. Basically, the way that this works is that the soil temperature varies from the average annual ambient air temperature by some certain number of degrees depending on the depth below the surface of the soil. You can see in this image on the left that the soil temperature will equal the annual ambient air temperature at a depth of 30 feet below the surface and will vary from positive or plus or minus 21 degrees Fahrenheit at the surface of the soil. In Rexburg, Idaho, you can see on the map on the right, our average annual ambient air temperature is 42 degrees Fahrenheit, or 10 degrees Celsius. In order to keep the greenhouse above freezing, we would have to go plus or minus 9 degrees Fahrenheit from that average annual ambient air temperature, which occurs at a depth of 8 feet. However, for best results, to get the highest soil temperature, we would go down to that 30-foot depth where we can get a 42 degree Fahrenheit soil temperature. So we ran an energy balance to determine the heat loss from the greenhouse and pipe parameters to match that heat loss. On the left, we have energy loss, which occurs due to convection and radiation and results in a total of 2.875 kilowatts of heat loss. In order to match that heat loss from the piping system, there are three controllable factors: the pipe diameter, the airflow velocity, and the pipe length. In this example that I have on the right, we assume a 1 meter per second airflow velocity and a pipe diameter of 0.15 meters, and we determined that that would require a pipe length of 56.7 meters. We could alter any of these three parameters to determine the optimal airflow velocity, pipe diameter, and pipe length to reduce the cost of this heating system. 56.7 meters is a lot, and the length of the pipe actually has the greatest control over the overall cost of the heating system. So we're seeking to minimize the length of the pipe. From this graph, you can see that as the pipe diameter increases, the necessary length of pipe decreases. However, the rate of length decrease with respect to diameter decreases as diameter increases. So there's a point at which a big change in diameter will make only a small change in length. Also, with these larger size diameter pipes from commercial pipe vendors, the step size, or the difference between pipe sizes, is really big, and the difference in pipe costs is really big as well. And so we determined overall that the optimal pipe diameter is actually 0.3 meters. So I did the same with velocity, and you can see that as the velocity increases, the necessary length of pipe decreases as well. So in order to get a really short length of pipe, or at least a short enough length of pipe that we can do this project without needing 50 or 60 meters of pipe, we just need a slightly higher airflow velocity and a slightly larger diameter. After running through all the numbers and optimizing everything, we determined an optimal pipe diameter of 0.3 meters, an optimal airflow velocity in the pipe of 2 meters per second, and an optimal pipe length of 19 meters. With these three values, we do reach that 2.875 kilowatts of input energy that the greenhouse loses, so we can maintain a constant temperature and have the lowest cost of piping. Just to be clear, this image is not of our project. This is someone else's greenhouse project, that from an article that we were reading about someone else doing a similar project, and this is the piping system that they chose. Ours would be a similar piping system with similar depth, similar length of pipe, and with fans to create that airflow velocity inside the pipes. To finalize our project, we've performed a cost analysis to compare heating system with electrical heaters, as shown on the left, with a heating system from a subterranean piping system, as shown on the right. With a heater installation, in addition to the cost of the heaters, you would require electrical costs approximating $60 a month. With the subterranean piping system, you do need a large initial cost. We've determined about $616 plus a backhoe to dig the hole. Now for us, that's a little easier. We can borrow a backhoe from a friend or relative, and all the manpower can come from within the family. And so the installation cost is pretty low. The cost of the pipe, $616. And so the subterranean heating system will actually pay for itself just in terms of month-to-month cost, and about 20 months compared to an electrical heating system. And that's assuming that the electrical heating system would only be in operation for half the time. So overall, it would be much more cost effective to use a subterranean heating system, and it's actually not too expensive and totally plausible. I think this would be an exciting thing to do for greenhouses. I know there are people who have used subterranean heating systems for greenhouses before, and that subterranean greenhouses themselves, where you put the entire greenhouse underground, are sometimes used. And there's a guy in Shelley who grows orange trees underground. So it's totally doable and not too expensive.